Okay, so hello everyone. Thank you, Bastien, for the possibility to have this seminar, to join this seminar. Bastien Chapuis, he is a research engineer, senior expert in SHM. He's the of the subcommission SHM of International Institute of Welding. And obviously is interested in guided waves, passive methods, and optical fibers. So that's why he proposed to talk about the topic of today, that is development of a passive tomography system for corrosion monitoring. So I think, as you said, Bastian, it strongly deals with robustness against environmental and operational conditions, ambient noise correlation, and use of FBG, which are all topics which are strongly linked and related with our doctoral consortium with USES2. So thank you very much for this seminar. And
okay, but thank you, Luigi, for the introduction, and thank you for the invitation. So, as you mentioned, today I will cover several topics that are linked with USES2. Especially, I will present you the work performed in the past years. So it's almost 10 years to develop one system we call passive tomography, for especially for one application, which is corrosion monitoring in pipes, but it can have also other applications. We'll see. So different people have been involved in this work. Here I have credited my colleagues Arnaud and Tom, which are the main researchers in the field at CEA, but in practice there are many other people involved at CEA and also in other institutes that allows us to progress on this topic. So do not hesitate to interrupt me if you have any question. I have a few slides, but if you want to ask some questions, don't wait the end and don't wait that people all sleep. Ask the question when you have. Don't worry. Well, you're probably all aware, and probably all of you visited CEA during the first meeting of USES2. So CEA, we are research public organization in France, a big research center in France, and we belong, my colleagues Tom, Arnaud mentioned in the previous slide, and myself, at CEA LIST, the Digital Technology Institute of CEA, more precisely in a department that works on non-destructive evaluation techniques and structural health monitoring. I will not describe more in detail this slide. And in our lab, so it's a lab called Systems and Photonics for Monitoring. So title very linked to the topic I mentioned before. We work mainly on two main technologies, elastic guided waves and optical fibers, with different types of sensing with optical fibers, FBGs and distributed sensing. We develop full SHM systems, so we work on sensors, we work on optoelectronic systems, data processing. It can be also embedded data processing in the systems, and two other topics to qualify the system. So the first one is a performance demonstration, to demonstrate that we will detect with our systems targeted defects. And another topics, but I've already mentioned that during the previous meeting, environmental assessment of SHM systems. And you will see here some photographs, but we will see more in detail these applications in my presentation. You're all aware about structural health monitoring, so I will also skip briefly these slides. Just to say that we want, let me just change something. We want to determine the health of the structure until the next maintenance operation. There are different fields of application of SHM. Initially, it was mostly civil engineering and aerospace, but now it's widespread in industry. And there are different technologies that are used to achieve these objectives. And one of these major technologies that is under investigation in several laboratories in the world are ultrasonic guided waves. There are other technologies, but there are different academic researchers and laboratories in the world that are working on ultrasonic guided waves. Why? It's because these waves can propagate along large distances with low attenuation. So with a limited number of sensors, you can cover pretty large structures. You've seen that my previous talks about rail, that with 2 sensors, we can monitor 1 kilometer of rail, for example. The difficulty with guided waves is, but it is also their beauty, is that they are complex. There are a lot of physical phenomena that are involved in guided wave propagation, dispersions, multiple modes, etc. So we, especially at CEA, we rely on simulation to design our SHM system. And classically, we use the piezoelectric sensors to emit and receive the guided waves, but they are not suited for harsh environments. They have limited performances, limited robustness, especially at high temperatures, and the electronic systems and wiring can be cumbersome. So for the integration in some critical applications, for example, aerospace, where we need to reduce mass, lot of cables that are necessary for piezoelectric transducers might limit some deployment. That's why since around 10 years, we are working on at CEA to use FBG, so fiber Bragg rating sensors on optical fibers as sensors for guided waves. And we will see in the presentation why we think that this type of sensor are very promising for guided wave based system. So today I will coming back to the title of my presentation, I will describe what we call the guided wave tomography system, how it works, and we will especially describe an algorithm that doesn't require baseline. I will explain you why we think that it is very important for SHM, and we will demonstrate that this guided wave tomography algorithm without baseline is capable to operate in very variable environment, especially with very large temperature variation ranges. Then we will have a second part about passive acquisition. So in the title, it was passive guided wave tomography. So I will describe you what is the difference between active and passive systems. And we will show you a demonstration performed by our team in a few years ago in a erosion loop to demonstrate that passive guided wave tomography was able to monitor very precisely the erosion in a metallic pipe. And then we will finish with fiber Bragg ratings with our recent development of FBG systems to measure guided waves and how all these sensors can be coupled with a passive guided wave approach shown in the first two parts. So let's start with guided wave for corrosion monitoring. So corrosion in pipes, it's a very common phenomenon in metallic pipe, and in several critical industries, it can lead to very severe problems. Especially, you've probably heard that 2 years ago in France, we had a major problem of corrosion in nuclear industry. We have been obliged to shut down tens of nuclear power plants in France, and it costs to EDF, the French company, a lot of money due to the detection of this corrosion. Usually, corrosion is detected by using ultrasonic, non-destructive testing system with a ultrasonic volumic system where we can measure the thickness of a pipe just below the probe. So the main major drawback of this approach is that you have only a limited zone of your pipes that is inspected, or the inspection is very, very long. So to overcome this limitation for SHM application, so where it's not an inspection by a periodic inspection by an inspector, but for monitoring system, we have also possibility to use long-range guided waves in the pipe. So we emit through a ring of piezoelectric transducers a wave that can propagate tens of meters from this probe, and when there is a thickness reduction, thanks to corrosion especially, a wave is reflected back, and we can detect that. The difficulty of this technique is that in general, it's very difficult to have quantitative measurement of the corrosion with this long-range guided wave. We receive an echo, but it is very difficult to link the amplitude of this echo or characteristic of this echo to the rate of the severity rate of the corrosion. So our objective was really to develop a system that is able to give residual thickness, absolute thickness of the pipe with a permanently installed system. So for that, we don't use long-range guided waves, but we use what we called medium-range guided wave. So other type of modes. We propagate on shorter distances, so it's not adapted to cover hundreds of meters of pipe in a nuclear power plant, for example. We can detect only, monitor only critical sections, but we will provide by the tomography, guided wave tomography algorithms, absolute thickness. So we can precisely measure the evolution of the corrosion in the pipe with our system. So for that, we installed 2 rings of transducers that these 2 rings surround the critical zone we want to monitor. And typically, we can cover distances that are of the order of 1 meter. It's linked to the diameter of the pipe. It's a few diameter of the pipes we can cover with this type of approach. And one important thing, I will describe you why it is important later, is that the algorithms we have developed doesn't require baseline signal. Generally, with guided wave tomography algorithms or other guided wave algorithm, when we want to perform SHM, we need to perform what we call a baseline signal, so an acquisition of the signal when we install the system, and we make the assumption that the structure has no defect at this stage, and then we monitor the variation of this baseline over time to detect the defect. The difficulty with this approach is that the variation of the signals can be linked to a defect, but can also be linked because by environmental or operational conditions. For example, variation of temperature, variation of stress on the structure, etc. So it's very difficult to separate these effects, and the consequence is that a system based on baseline can send a false alarm, which are very problematic for the acceptability of the system, because an industry, when they install an SHM system, they don't want to get a false alarm every week. For example, in a nuclear power plant, you cannot send operators every week just to cut off the alarm. So we wanted to develop a system very, very robust against environmental variations, and that's why we worked a lot to develop this approach without baseline. So more in detail, how it works, guided wave tomography, first active, and then we will see passive. So there are two main steps. The first one is data acquisition. So we have our two rings of transducers. Here it's piezoelectric transducer. It's these white dots here on the pipe. And we have here an artificial flow. It's a corrosion made by electrolysis on a pipe in our lab. So we make the acquisition. So the acquisition, we make full matrix capture acquisition. So we recover all the signal possible with using one emitter on one ring, and receiving all the signals on the transmitted on the other ring, and then we make all the combination between emission and receiver. So we have a lot of signals, and then the second step is to process the data, and the process gives us a quantitative thickness map of the structure. So we convert the information that are here in terms of time of flight, phase, etc., into a thickness map. And it is a quantitative thickness, so it's an absolute value here in millimeter for the full zone between the two transducers. For that, there are different algorithms that can be used to make this inversion. All the results that I will present today is based on a simplified model for elastodynamic propagation. So we make acoustic propagation hypothesis using the Helmholtz equation. We are currently working on a more complete algorithms. It's a current PhD thesis that will end in 1 year with to improve the resolution of the tomography and the applications that we can cover. But all the results I will present today are based on this approximation, acoustic approximation. So with this approximation, we have one strong assumption is that there is only one mode that propagates in the structure, in the pipe. We will see other application on plates, but we always made the assumption that there is only one mode. And we use the dispersion curve of this mode. So we have to select on the dispersion curve one mode, and we use the dispersion curve of this mode to invert. So in practice, when we have our signals, we want to invert this, and the algorithms give us this value k, which is a wave number, and this wave number we invert this wave number thanks to the dispersion curve of the selected mode to convert this value in wave number as a thickness map. The advantage of this acoustic approximation that we have a very, very fast computing, and we have not yet implemented it inside the electronic system, but we are currently working on it. So this type of algorithm can work on embedded system. So, but the limitation is that the resolution of these algorithms are limited, so we can image only extended corrosion defects, or maybe the term that is more adapted is erosion. So it's not pitting corrosion, very small corrosion, very small pits of corrosion. It's large area, typically of the order of magnitude of 1 centimeter. Because we do not, with acoustic simplification, we do not take fully into account the mode conversion effect at the defect, so the diffraction effects, etc. So we lose some resolution due to the assumption of the wave interaction with the defect, and that's why we are working on more precise algorithms for other applications. But for many applications, this approximation is very convenient, and we will see that it works very well. And as I mentioned, we can work without baseline signal. So the main advantage is that we can work in variable environmental conditions, and we can also work practically on imperfect industrial structures. So structures that are already aged. For example, we can install our system on pipes that has already some corrosion. And we give the absolute value of thickness, so we give the actual loss of thickness due to corrosion. We just don't give a corrosion rate, the progression of the defect, but the absolute value. So you will have some more details about how we can obtain these baseline-free algorithms in some papers of my colleague Tom Rouet. This one, but also other, or in his PhD thesis. But I will now describe you some experiments and some development we performed. So during several years, we have told that our algorithm is robust with respect to environmental conditions. But we have, in reality, demonstrated it only very recently. So it's something I will show you now. So we performed this experiment in our climate chamber at CEA, where we have put our structures under a varying, a large range of temperature variation between minus 20 degrees up to 50 degrees. So we did not work on a pipe because the climate chamber is too small. So we work on a plate, but the idea is very similar. So the tomography is performed by emitting with one sensor and receiving by all the sensors of the ring. And we get at the end a thickness map of the zone inside this ring of transducer. So here we have a 3 millimeter thick aluminum plate. We use 48 piezoelectric transducer. So it's quite a lot. So we see here a large number of cables, etc. So compared to my previous first affirmation that with guided wave we do not need a lot of transducer, it's quite wrong. But in practice, it was also to test the limit of the algorithms. We can, in practice, use one sensor over 2 or one sensor over 3 without too many degradation. We worked here at 50 kilohertz, which is quite low, and we will see why we work at so low frequency in the second part, in the passive chapter, which has we could increase the resolution by working at a higher frequency, but it's really a choice made by our target to work on passive system later. So this so low frequency. Like in pipe, we created our defect using an electrolysis setup. And here we have in this experiment performed 3 different depths on the progressive defect on our plate using masks to protect the plate against acid liquids that were installed on it. And you see here some thickness maps that are not recovered by our piezoelectric transducers, but using an optical system. It's a system called GoScan, and this optical system can give us a very precise thickness map of the structure. So it's our reference measurement is obtained with this system. So for the 3 different defects. So here are our reference map, and we show here the absolute tomography. So when I say absolute, it means without baseline. So we don't need a baseline. We use an auto-calibration algorithm, and we produce this type of images. So we see here that, as I mentioned, we can get the main geometry of the defect, but we have a limited resolution to get the very thin features within the defect, which is not really a problem, because what is important for the security of a pipe or of a plate is really the remaining thickness, so the maximal thickness of the corrosion, and we capture it very well with our algorithm. We will see some cross section to be more quantitative just later. So here are the cross section for the 3 different defects. So it's a horizontal cross section with this line, if you see my mouse, and we have in the dotted line is a reference measurement using the GoScan scanner, and here in color are the reconstruction with our tomography algorithms, and the reconstruction at different temperature. You can see that for all the different temperature, we have very consistent results. We capture mainly the geometry of the defect, and there is not a lot of variation between the different estimation at different temperature, even if we have a very large temperature range. Here we have 70 degrees of a temperature range, which is and this is possible thanks to the auto-calibration method that I mentioned earlier. If we zoom.
Excuse me?
Yes?
Can I ask something?
Yes, of course.
How you explain the robustness with the temperature variation?
It's really because we do not need, for example, here we have, when you have the line at 50 degree, you need to obtain this thickness map. You need signals that are measured only at 50 degree. And our auto-calibration method in practice detect the paths that are defect-free. So, for example, the algorithm detects that this path contains a defect, so it won't be used for the calibration, the system calibration. It will the calibration algorithm will use only the path on a pristine area. Then it will compensate the difference between our acoustic model that introduce a bias in the theoretical signals, and the calibration compensates the bias due to the limited model with what we observe we measure with the system. And since we capture with this calibration algorithm all the zones that are all the paths that are defect free, and then we use that to calibrate, and it works in practice very well.
So that means if the two sensor rings aren't at the same temperature, the auto calibration is not going to work.
So far, we have not tested this approach in structure where there is a gradient of temperature.
Okay.
So yes, it can be a limitation. But it's not true. We have partially tested with gradient of temperature, so not on this plate, but on pipe. If I come back here, we have produced images on pipe where there were pipes that were outside, so there were sun, and with the sun, the top of the pipe is hotter than the bottom part, and we can partially compensate this effect, and we see some very good images also with this type of check. But here we have the same temperature between the sensor here and the sensor here. We have not yet explored configurations where there are very different, very huge gradient of temperature within the structure.
But since it's only for 1 meter, it's not that pertinent, right?
Yes, I don't know for all the configuration, but in practice, for all the applications we had so far, it's very, very robust. So if we zoom on this cross section, we see a small variation due to temperature, especially on this artifact, but also on the most important zone, which is the center of the defect. This is due to the here we use A0 mode on this particular case, and with temperatures, Young modulus varies, which have a variation of speed, which is explained by the group velocity dispersion curves, and this variation introduces a small variation in the thickness. A possibility to compensate to have better results would be to use the dispersion curve at the correct temperature. Here we have not measured the temperature, so we have used the dispersion curve as 20 degrees for each image of this each cross section here. We probably could use the right dispersion curves in order to better compensate this small variation. But in practice, this is really of the second order compared to the real thickness of the defect. So it's not necessary. We cannot. You see that we have still 0.1 millimeter or 0.2 millimeter precision. We will improve from of second order, so it's not necessary to do that. But why not? Just to compare, here we have absolute tomography, so with auto calibration method. If we used relative tomography, so using the calibration with a baseline at minus 20 degrees, you can see that there are some offset, which is due to the incorrect signals that are used to compensate the variation, temperature variation. Yes, sure.
So the relative tomography means that you choose a specific baseline to do the calibration, right?
Yes, exactly.
And it produces an offset, basically.
Yes.
Okay. Whereas the auto calibration doesn't let you depend on a specific baseline.
Yes, exactly.
Okay.
Yes. The baseline here, so it means that we used signals obtained measured on the defect-free pipe, plate in that case. So we make the assumption that there is no, all the thickness of the plate is nominal, is a nominal value. In practice, when we have even on a new structure, for example, a pipe that has just been manufactured, there are already some variations of thickness of the order of magnitude of 10–15% of the thickness of the pipe. And we will see exactly on the next chapter, that is just after this slide, an example where we installed it on a real pipe, the system, and even without performing some corrosion, there are already some local thickness reduction. So if you use that relative algorithm, you can miss this value and you can already have lose 10 or 15% of the thickness without any defect. It's something very important to know to give a very precise result.
Thank you very much.
So here, all what I have presented so far is active tomography. So we use I will just show you that. I use one piezoelectric transducer to emit the wave in the structure, and other piezoelectric transducer to receive it. So as I mentioned, it's full matrix capture acquisition. So we make all the different combination between emitter and receiver. But if we consider only two transducers, we have this typical signal. So in blue, positive time, so it's emission in A and reception in B. And in black here, it's a negative time, it's just a convention, emission in B and reception in A. And these are the signals that are, in practice, we just use positive time with our algorithm, but it doesn't mind. These are the signals that are introduced in our tomography algorithms to produce thickness map by characterizing the time of flight of this wave packet and the phase difference of this packet. What we mean by passive acquisition, it's a different way to proceed. We do not emit wave in the structures. We use only receiver of elastic wave, and we measure the ambient noise of the structure in operation. So on an aircraft, the noise can be due to turbulences on the fuselage or due to vibrations of engine. In a pipe, it's typically the circulation of the fluid inside the pipe. And all this effect can create some mechanical waves propagating in the metallic structure due to fluid structure interaction. And so we have very low amplitude elastic waves that propagate in the structure. So here in our pipe, and with the passive setup, we measure this ambient noise. Typically on directions that are very large compared to the ultrasonic phenomena we want to capture. So ultrasonic phenomena, it means the time of flight here. So times that are largely above millisecond, I would say. So typically we measure 10 seconds of noise. And we measure, what is important, it's to measure it simultaneously in A and B. And then we correlate these two signals. There are also other algorithms, but it works very well with correlation. We'll see some limitation, but we correlate these two signals, and by correlation, if we respect some hypotheses, we obtain this type of signals that are very similar to the previous one. So we have in positive time of our intercorrelation the propagation between A and B, and in negative propagation between B and A. And you can see that you can identify almost the same wave packet. Here we use typically this one, the first wave packet. There are some residue here that are what we call the correlation residue. But the information that is important for tomography algorithms is in practice very well captured. And we use this, so this intercorrelation signals as a starting point for our tomography algorithm. There are different theoretical papers. I refer here to this one. There are a lot of literature about this, why it works, why it doesn't work in many situations also. The major hypothesis that can be problematic in some industrial configuration is that we need equipartition. So the noise must come from the different direction, and with some consideration about repartition of frequency and equipartition of energy and frequency, etc. So I mentioned that it's because, for example, in a fluid, in a pipe, we have a privileged direction for the fluid circulation. Or on an aircraft, we have the aircraft is moving in one direction, so we have more energy traveling in one direction than in another one. So that can, in this situation, lead some less performant convergence of the correlation towards what we call the green function. And we will see some results where we illustrate that. So why choosing active or passive? Active method, it's much more common, and it's mainly because in NDT applications, we work only in active method in general. And the main advantage is we can really select our frequency of operation, so the wavelengths, so to target the best resolution, the best frequency to get the better resolution of our imaging algorithms. And if the environment is not noisy, we have very clean signal. In SHM, we would like to use our system in a structure in operation. So we do not want to stop the circulation of the fluid inside the pipe, for example. And the noise will perturbate the acquisition. And in reality, we will use the noise for our passive method. So the more noise we have, the more the correlation converge towards the green function. So we love noise in our passive approach. And since we don't need emission, because we rely only with existing elastic wave in the structure, we can simplify the electronics. We do no longer need emission circuitry. We can reduce, but it has to be demonstrated that is really true in all the situations, but in general, we can reduce the power consumption of our system. So for monitoring systems that operates on battery, it can be an advantage. And the main reason why we developed that approach at CEA is because we can use sensors that are not able to emit waves in the structures, and typically fiber Bragg ratings on optical fibers, with a lot of advantages I will describe in the third chapter. So results that are quite old now in our group, but it was our first work on the subject, just to demonstrate that it works well, this equivalence between active and passive in a practical operation. So here we consider a plate, an aluminum plate, and we have a piezoelectric transducer at different distances. So the transducers are not moving as in the animation. In practice, we used a circular ring and we just select a couple to have different distances. And the noise is created using compressed air jet that is sprayed at the surface of the plate. So the air jet created some turbulences, and these turbulences create some very small amplitude elastic waves in the structure. We measure the noise with simultaneously with all the transducers during 10 seconds, and we have the results here. So for different distances between the sensors, in blue the active signal, so the reference signal. So we have one wave packet here, so it's A0 mode that propagates from A to B and from B to A, and so for different distances, and in red we have the correlation. So we see here that we can very well recover the time of flight of A0 mode in this with this passive approach. So here it's a lab measurement, but we'll just show you another experiment we performed more recently on a more realistic application. So here it's a rail. We have a rail that with 4 sensors at different distances, and we have a train that is moving and passing from above the sensors. So we capture with these 4 sensors these 4 signals, which have quite a large frequency content, which peak at very, very low frequencies, a few kilohertz for this one, for example, or tens of kilohertz. Typically, we worked and we are interested to detect our defects at 40, 50 kilohertz. Here's the range of. So we have filtered this signal to process the noise only in this range between 30 and 50 kilohertz. And we have reconstructed here the guided wave propagation. So it's a peak. So it's really the wave that propagates between, so here at 40 meters, so between C1 and C2 or C2 and C3, I don't remember. And you can see here so that we can very well capture the wave that is propagating between these 2 signals without emission of waves, just by processing the noise. And as I mentioned before, here we have not equipartition of the noise because we have a train that is traveling in one direction. And we have reconstructed only the wave packet traveling in the negative time, in this direction. So we do not fulfill exactly the equipartition hypothesis for the convergence towards the green function, so the reconstruction of the full signals in both negative and positive time. But for practical operation, we capture here the wave propagating between the different sensors without emission of the wave. So if with this type of system, we could imagine detect broken rails between the different sensors, but just by processing the noise. So for those who have followed my presentation about rail monitoring system a few months ago, in practice, we didn't work with passive system. We developed a fully active system, but for different reasons. But with these experiments, we've shown that theoretically, fully passive system could also work very well. You see here that we have a very, very good signal-to-noise ratio to detect the wave propagating between the different sensors. So this slide was really to illustrate that we are not obliged to fulfill this hypothesis of convergence that seems very strict, equipartition of energy, even in very, very directive noise, the system works very well. Now, come back to our application on pipe. In that case, it was a more recent PhD student, Tin Wang, that finished his PhD 4 years ago. We used here fluid circulating in the pipe. So in his experiment, he used still compressed air jet sprayed internally in the pipe and measured simultaneously the noise here on 2 rings of transducers. You have a short window of noise with very bad signals. It's not just noise, and the frequency content of this noise. So we see that we have some energy until 200 kilohertz, I would say, even if we work. But the main energy is at lower frequency, around 50, below 100 kilohertz, and that's why I mentioned earlier that we worked at low frequency. Typically, active tomography systems, they work at several hundreds of kilohertz to have better resolution. Here we work at lower frequency. It's because in practice, if we want to apply our tomography algorithms on passive signals, we would have energy only at low energy. And the typical signals we want to reconstruct, or here it's active signals, we have, here you fix one emitter, and we have all the received signals on the opposite ring. And you can see the first wave packet is the direct signals. So if the propagation is aligned here, the two transducers are aligned, there is a small travel time, and if the reception is moving around the ring, you can see that the path is slightly longer, so the time of flight is slightly larger. And then we have helical waves that make one round before coming from A to I. So we have the first helical waves here, and then the second, so 2 rings before turning, etc. So it's the typical signals we want to reconstruct. So here you are. So here it's yes.
Why we're talking about active?
It's just a reference, just to show that
what I'm expecting.
Yes, what we want to demonstrate that passive, we can reconstruct the same information or some important information as in active. And especially here, the arrow indicates the direction of the airflow that is sprayed inside the pipe. So here we have in the axis of the pipe. Here we have in the axis, but moving around circularly, and here it's out of plane excitation, I would say, with compressed air spray. And you can see here that with this first 2 excitation, we reconstruct only the direct path, the first wave packet in both directions, positive and negative time. And here with this excitation, we can reconstruct also the first helical, probably also second one, but just in one direction. It's not what I wanted to illustrate here is that the source of excitation can limit which type of information we can recover in passive. As in the case of the train, we do not recover the full signal. So we have, when we develop a passive monitoring system, we have to be sure that the source noise that we will use can give us the wave packet we want to use in our algorithms. So in practice, with the monomode excitation, monomode assumption, acoustic assumption for the tomography algorithms I have presented previously, we use only the direct path. So each type of source could be sufficient. But for some imaging algorithms that use also the helical path, that can be used to improve the resolution of the algorithms, we have to be sure that the the source of noise can create this, can also generate this helical signal. Well, I have mentioned that to process the noise we used correlation. In practice, and refer to 2 different papers, we can also use another algorithm which is called passive inverse filter, which works very well, especially where there is a lot of transducers. So it's very well adapted for tomography. In practice, here you have a frequency time sketch of our reconstructed signal. You can see here that, so in color, we have the power spectral density that is reconstructed by the correlation, cross-correlation. And you can see that we reconstruct mainly the low frequency in this case. With this passive inverse filter, we can reconstruct largely in a larger frequency range. It can also better equilibrate the influence of the different frequencies. So if you are working in a configuration where there are a lot of sensors, it can be a good option to work with this passive inverse filter, so more complex algorithms than a simple correlation between sensors. And the application is so I mentioned. I've shown previously some measurements on the plate. So here we have sprayed the air jet on equivalently in all the position and direction in the plate. So here you have a thickness reconstruction of for an artificial defect here. So it's a good. You have not a reference map, but you can trust me. It's a very good reconstruction here, using correlation algorithms and tomography algorithm. But in the second situation, we have sprayed the compressed air only on the half of the plate. So we do not fulfill the hypothesis of equipartition. And in that case, the correlation has worse results than previously. There is a degradation of the algorithms, and using passive inverse filter, we can partially compensate this lack of equipartition and come back to better. It's not perfect. We have less. We have some artifacts here, for example. So it's worse than the previous case where we have a full convergence due to the equipartition, but in that case, it can save some convergences using a passive inverse filter. So let me finish this part with an application on a representative setup. So here we performed some accelerated erosion tests on the air sand flow loop. So here you have a photo of the loop. We have a vessel which is full of sand, and then we inject the sand in the pipe, and at some point the pipe is expected to be eroded by the propagation of the sand in the pipe. So there are a lot of sand in practice to have accelerated erosion. So it's experiments of 3 hours. 3 hours of several 700 kilograms of sand traveling in the pipe, and what is expected is to lose almost 0.1 millimeter of thickness per batch. So we have installed our instrumentation system here just after an elbow, because it was expected to have a high erosion rate at this place. So we have 2 rings of transducers here. So there are a lot of cables. There are also optical fibers or other instrumentation, but here we have 2 rings of transducers, and we worked inactive. We will show you some no, I have not found some active results, but we had active maps at 90 kHz, and in passive, we measure the ambient noise that is mainly produced by the sand impacts on the pipe wall. So in practice, the sand is supposed to follow this this trajectory. So we have a maximum erosion at the top of the pipe here. So if we and here you have the results. So it's a thickness map. So you can imagine you have in red the transducers, the touring of transducers. So we have unfolded the pipe, and we have in yellow the expected trajectory of the sand. So we have here some the images that are acquired. So it's 60 seconds of noise that is processed at different steps between the different time during the experiments. So there were several batch of sand that were sent in the pipe, and you can. So if we come back at one, so at the beginning you can see that there are already some zones that are that have lower thickness. So it's, as I mentioned, is even on a pristine pipe of a new manufacturing pipe, there are already zones that have lower thickness. So our absolute tomography algorithm captures this initial thickness reduction, and you can see here that progressively this zone is the thickness in this zone is reducing due to the erosion. So we have compared, I think we have some cross section, but we have compared this the results produced by these tomography algorithms with reference measurements performed between and after the experiments, and the erosion rate is very coherent with what was expected and what has been measured at the end of the experiment by using classical ultrasound. Yes, but we have here the cross section. Sorry, it's a cross section in blue. So we have in blue it's are the cross section at the beginning of the experiments, and the time being you can see the thickness reduction in this cross section. So we can very precisely monitor the thickness reduction due to the sand, and fully in passive using passive measurement. So as I mentioned, the ID behind this why working in passive is we really want to replace this very intrusive system, lot of wires, by only one optical fibers with several FBT sensors. Working in FBT can work only in passive as a receiver of sensor. So that will be my last chapter.
May I ask you?
Yes.
Can I ask you two things?
Yes.
Speaking about thickness resolution, can we say that?
Yes.
What is the data?
But typically,
let's say 0.01 millimeter as a resolution. It seems that can be detected by this system.
Yes, but we can see some. What I've not really precise here is that you have this first blue line. Is that there are also strong temperature variation in during the measurement, because the sand due to the sand impact, the temperature of the pipe wall increases during the experiment. So as I mentioned previously, studying when we wanted to demonstrate that we are robust against temperature variation, there is still a small variation of of our reconstruction due to temperature. So I don't think we can claim that we have a 0.01 millimeter thickness resolution.
Okay.
It's probably worse than that, but still we have here a very robust measurement, and we can clearly see the thickness reduction, and we will for sure capture the defect before we reach 0.
Okay, thank you. And could you tell me more in one moment, another time, about the passive inverse filter you mentioned before? What's that?
Yes. So when we work with correlation, we have here, yes. So in correlation, you consider you emit, you process the noise. You make the correlation between the signal A and B, intercorrelation between A and B. So you consider all the couples, emitter, receiver, separately. And you process sequentially A and B, A and C, A and D, etc., making all the different intercorrelation. With the passive inverse filter, the idea is to process all the signals simultaneously. So we make a matrix of all the signals, and then we make a decomposition of etc. And with this processing, we capture better the small contribution of all the different passes. That's why it gives a better results.
Okay, thank you.
But the computation it's more demanding. So for an embedded system, so far we have not embedded. We have embedded our correlation algorithms on our electronic systems, but passive inverse filter not yet, for example. So as I mentioned, the idea is to replace piezo by FBG. So why FBG? So in general, optical fibers are studied in SHM, are widely studied in SHM because they can be integrated in many structures. So here you have an example of a composite vessel for gas storage, and on this composite vessel, optical fiber is wrapped during the manufacturing process, and we can monitor with this embedded optical fibers. Generally, it's used at a low frequency to monitor temperature or shape of the structure. What is less widespread using optical fibers is to use the optical fibers as sensors of ultrasonic waves, so at higher frequencies, but with very, very low amplitude deformation. So that's why at CEA we worked since a few years to the development of an optoelectronic system that is able to measure these ultrasonic guided waves using optical fiber sensors, and especially FBGs. So FBGs, I will just show you in the next slide how it works. There are widespread used to temperature measurements or strain measurements. It's less common to use it as a guided wave measurement. We will see that we have to be careful to use these FBGs when we work in varying environment. So I will try to explain how we compensate in the instrumentation system the variation of temperature of or environment of around the FBG. So FBG.
A question?
Yes.
On the previous slide.
Yes.
Is that the work of Laurent Marine or?
Yes, this curve is a work of Laurent Morin, one of our colleagues at CEA.
Yeah, because I work with Sylvain and Laurent.
Yes.
And I remember him showing me maybe part of this experiment. But was it made with optical frequency domain reflectometry, maybe?
So it's so I'm not familiar with what was really behind this, but it's for sure not FBG. It's not punctual measurement. It's
it's continuous.
Continuous measurement.
I think yeah. I just wanted to understand if it was made with FBG or not.
Okay. So it's not FBG, and if you want more detail, you have to ask to Laurent or see the publication. Sorry.
Thank you.
So FBG. So FBG are sensors that are placed on the optical fiber. So on the optical fiber, you have the core and the coating. We inject white light for or large band, different colors in the core, and the light propagates in the structure. And when the light rises on the FBGs, one wavelength is reflected, and the wavelength is linked to the period here of this FBGs. So we call the lambda Bragg, so the wavelength that is reflected and is directly linked to the lambda here, which is the period of this FBG. And we put the animation when there is some temperature variations due to dilatation, the wavelength varies, or if there is strain due to for a sensor that is glued on the structure, so strain at low frequency, for example, due to vibration, the lambda reflected varies. And that this is also this phenomenon that is used to capture elastic waves. So we measure the variation of this lambda at high frequency to capture the waves at high frequency of FPGs that is glued on the structure. So at CEA we have a platform called FemtoBrag that can be used to manufacture our own FBG sensor. So here you can see using laser femtosecond, we create some microvods in the core of the optical fiber. So here you see the core and the coating above and below, and the periodicity of this microvod directly create reflected lambda waves and lambda Bragg, and you can see here the peak that is that appears as long as we create the FBG inside the optical fiber. So this type of FBGs are adapted for very severe environments, especially because they are very robust against temperature variation, compared to other type of FBGs that are manufactured with other technologies. So we have tested it on very high temperature or cryogenic temperature or against radiations, etc. And as optical fibers that can be used, that can be integrated in structures, especially in composite materials. And the one main advantage is that we can use multiple we can create some multiple sensors on a single optical fiber. We can put one FBG at one point, and further on the optical fibers, we can put a second FBGs with a different wavelengths. So we creating a different period here. We can have a second peak at a different wavelength, etc. And then we can have several sensors on a single optical fiber, which is very convenient for a low intrusive system. So for higher, very high temperature, you can no longer use the classical optical fibers, but you can you have to go to sapphire fibers, for example, something we explore at in our lab for very high temperature. So as I mentioned, we can put different tens of sensors on one optical fiber, which is very seducing. The difficulty is then to interrogate all these different sensors. So I will explain you a bit how we interrogate it with our system, our optoelectronic system. So we have our reflected spectrum, so this Gaussian shape here. We put a laser, so at a fixed wavelength on the edge of the FBGs in this linear part. And when there is, for example, waves, elastic waves, that rise on the FBGs, this peak, this lambda Bragg peak, this Gaussian moves a bit. So the reflected amplitude at this part varies. So the reflected signals, so the reflected optical signals, is directly a mirror of the Bragg wavelength shift, or of the waves that elastic waves that arrives on the FBG. When there is, so I explained that with an elastic measurement of an elastic waves, but it's also the case if we have static or very low quasi-static variation of strain. So then we put here a photodiode that converts the reflected light into a voltage, and then this voltage is measured by numerized by analog to digital converter, produce a value that is saved. So with this setup, we can imagine to multiplex and demultiplex several sensors. So we have one laser for this Bragg, and we can put, if we have another Bragg at another wavelength on the spectrum, a second laser, etc. And we can put one sensor for each sensor, one laser for each sensors on our optical fiber. One constraint is that if there is a variation of strain of temperature, the wavelength lambda Bragg can shift due to temperature variation in the structure. So the lambda laser can be no longer adapted. So we have developed setting point tracking algorithms. So in real time, we adjust the value of the lambda laser to interrogate lambda Bragg to be sure to compensate the environmental conditions of our sensors. So for that, we used proportional integration control loop that is fixed on the low frequency variation of the output of the photodiode, and we fix that this DC voltage must stay between 4 and 6 volts. 5 volts is defined as the middle edge of the peak here. And to change the lambda laser, we use a Peltier, so a thermal component, Peltier source, that heat or cool down the laser. And by changing a bit the temperature of the laser, we change a bit its wavelength. So we can, in not real time, but we can track the variation of the lambda Bragg, so the sensor. We can track the variation of the sensor due to the environment in which we operate. So to test this principle, we have tested it with a mechanical 4 points mechanical test. So we have composite, small component panel here with 2 FBGs. One with to measure the strain that is created by this setup, 4-point bending setup, and one which is used for ultrasonic measurement and also tracking. Here I will show you some results on inactive, but it doesn't mind. I have presented before the equivalence between active and passive. So we work at 40 kilohertz, and we filter the signals, etc. It's not very important. And what is important here is that we have performed some cycles of bending at different velocities, at very low velocities at the beginning, 0.5 millimeters per minute, up to 7 millimeters per minute. And this low frequency strain induces a shift in the FBGs, and we want to our elastic wave measurement system to be able to measure the wave even if there is a low frequency strain in our structures. You can imagine to put this sensor on the wing of an airplane. You want to be able to measure the elastic wave even if there is a flexion, flexural, low frequency flexural wave of the wing due to turbulences or etc. So we have the results here. In blue is the results of our PI loop. So it's a DC output voltage of our laser. And we want to keep this blue line between the red dotted line here, between 4 and 6 volt. So, and in black here, we have the strain that is measured by the second FBG. So it's a mirror of the strain induced by the bending of the composite panel. So when the bending is very slow, you can see that we can easily compensate for the strain, and when it comes faster, there are some overshoots. So during a few seconds, the system works outside its operating range. The time that we use a Peltier, so a thermal component, to compensate the wavelengths of the laser. So it has quite a long inertia. So during it takes a few seconds to come back to the tolerated operating range. And when we are even too fast, the system is no longer able to come back into the operating range. So with this setup, we have characterized precisely the capability to compensate or no the varying operational conditions. We have to mention here that we have put here, we say that our target is to have normal operating range between 4 and 6 volt. In practice, if the DC voltage is between 2 and 8, we cannot see any difference in the ultrasonic signals that are measured. So we have a tolerance between with our PI tracking setup. But what we want to avoid is oscillatory, uncontrolled setup of uncontrolled setup. Here you have some ultrasonic measurements with this optoelectronic system. The first line is static acquisition, so where there is no bending of the panel, and you can see in blue the raw signals, and in red, which is slightly filtered, you can see that we have a very excellent signal to noise ratio, even without averaging. Here we have just one signal. We have no average of repetition of emission. We have just one signal, so excellent signal-to-noise ratio. And for the three other signals, these are captured with during the bending, so at a different point during the bending. And you can see that qualitatively we have quite similar signals. If we make the residual signals with respect to the static acquisition, so this line is this line minus this line is this line minus this line, etc. You can see that we have a residual that is of the order of 10% of the acquisition of the static acquisition, and no specific behavior. So we demonstrate that in that case we have been able to compensate the varying strain in the structure due to the bending. So of course here it's as I mentioned is between 2 and 8 volt. We have not I have not shown you some results here at point where we can no longer compensate. In that case, the signals are not are fully noisy. We can no longer measure the ultrasonic wave. Just an illustration, and I have almost finished, I think. Here are some capabilities to measure ultrasonic waves at very high temperatures. So we have put in an oven an FBG, and you have some elastic waves that are measured at 500 degrees. At the time where we performed the experiment, it was the world record. Now some teams have made measurement at higher temperatures, but we were very proud to have these signals measured at such high temperature at that time. And as I mentioned, so here you have some electronic systems. So the tracking box system is now implemented in this electronic board. So we have a optoelectronic system that is now able to measure and to compensate with 7 channels. So on 7 FBGs on the same optical fiber. And in the next years, we would like to increase the number of FBGs we are able to interrogate on the same optical fiber. Some of you are probably aware we also developed some electronic system in collaboration with Université Gustave Eiffel. So I see that Vincent Lecam is connected. We work with his team to develop a system called Geronimo to measure, but this is specific for piezoelectric transducer. And so we are currently trying to make the same type of system, but to interrogate optical fibers with embedded processing capabilities. Just to finish, if you give me a few more seconds, just to demonstrate that passive acquisition works well with FBGs. I have shown you previously this type of figures where we have different distances between 2 sensors. Previously, it was 2 piezoelectric transducers. Here we can reconstruct, so active signal is between 1 piezo and 1 FBG. Here in active, so it's in blue, and in red it's in passive. So we measure simultaneously the noise between the FBG and the piezo, and you can see that we can reconstruct the A0 mode in both directions in that case. And in these figures, we have 2 FBGs. We fixed the distance, and we just change the filtering, varying of the frequency filter, and you can see that we at different frequency we can reconstruct. So we have no active in that case because we have no piezo, but we can in practice reconstruct the dispersion curve of A0 mode. So it demonstrates that a fully passive approach works with FBG. And we have use this FBG sensors in fully passive system to image some defects. So here it's a defect on a composite plate. It was for an aircraft application. And here, similar configuration that I presented previously on a pipe with a corrosion on a pipe with an hybrid piezo FBG system. Why hybrid? It's because when we performed these experiments, we had not enough channels in our optoelectronic system. So that's why we had half of the channels, half of the sensor were FBGs and half were PZT. But the reconstruction we have at the end is obtained fully in passive mode. We do not use piezo to emit wave, just to capture. But I have explained you that it is quite similar. The performances we can expect with piezo and FBG in that case. So in conclusion, I have presented you some FBG measurement at different ultrasonic frequencies with a optoelectronic system we are currently developing, which is able to operate under a varying environment. I explained with you with the bending compensation, and coupling this FBG measurement system, we are able to produce some quantitative passive imaging of corrosion. We have not yet demonstrated a fully FBG system or passive quantitative imaging of corrosion. We have so far demonstrated capability to monitor corrosion with a fully piezoelectric system and with an hybrid system piezo FBG. And when we will have enough channel on our FBG measurement system, we will be able to do a full FBG system for passive imaging of corrosion. So in the current work in our lab on these applications is to improve our electronic systems. I have mentioned also some work to improve the guided wave tomography. So far, we used an acoustic model for the propagation of the wave in the structures, which has a lot of hypotheses. And in the current PhD work, we use a full elastodynamic model to properly capture all the wave phenomena that are involved in the wave propagation and wave interaction with defect. And with this approach, called the shape derivative, in the PhD, we can deal with more complex geometries, especially to monitor corrosion under supports on the pipe, which are the critical application of critical zone where corrosion appears on the pipe. And there is also another current PhD work to model what the fluid structural interaction, which is at the origin of the noise in the structures. I have explained you a bit with on the pipe with a different direction of noise of the earth, or the compressed air that is sprayed at the surface of the noise. That we cannot always create the waves. In the structure, we have not always all the waves that are necessary for to detect the defect. So we are currently working on the modeling of this passive noise sources to better characterize in which type of situations we can work with this passive setup. We can imagine, for example, that the system can work in pipes where there is a lot of turbulences, but not when there is laminar flow, etc. So this type of characteristic we want to extract. Okay, so I have finished. I hope you are still not dead. So if you have any question, please do not hesitate.
Thank you, Bastien. I have some questions.
Yes.
Since I'm working on a readout for FBG at CEA with Sylvain, I was wondering, I'm interested most in the frequency of interrogation of the Bragg that we are looking for this kind of application. At the beginning of the third chapter, you said that for active monitoring, okay, of course, I should interrogate my Bragg rating with a frequency that I am expecting in the emitted sound wave from the piezo, okay? And we are around, maybe I've lost some value.
But in active, typically until 500 kilohertz.
Okay.
But
in passive,
in passive, the frequency range is really linked to the source of noise. And when it is compressed air, so you can imagine some application on aircraft. Here you can imagine to work until I show you until 200 kilohertz. We still have enough noise. We have measured some noise until 200 kilohertz. Typically, when it is water, it's at even lower frequency, and we have until above 100 kilohertz. We have not yet at least capture some noise that can be exploited. That's why all our imaging algorithms are designed to work at a maximum of 50 kilohertz. So if you develop a system that is able to detect waves at 50 kilohertz, we would be very, very happy.
Okay, so
even if you don't reach 500 kilohertz, it's not a problem. We have application at 40, 50 kilohertz.
So supposing to reach 50 kilohertz, after 50 kilohertz, it's better to increase the resolution than the frequency. Do you agree?
Which type of resolution?
Of the wavelength shift.
Yes, but above 50 kilohertz, we need to improve the sensitivity of the system. So I'll just show you. Here you have the noise, but it is measured by the piezo. But piezo also have a filtering effect. So, but here above at this part, you have low energy of the noise, so probably very, very low amplitude elastic waves. So you have to be you have to improve your resolution in your measurement system at this point.
No, I don't get that. No, I'm asking the impact of the wavelength resolution in the Bragg shift.
Okay, so let's go maybe on this slide. So here you means that so your Bragg wavelength shift is here. What you measure is here. Is this reflected signal? So what you mean is that you need to improve the resolution when you capture this this wave.
Yeah, of course, I'm looking for increase the resolution. But if we said, for example, that a good system could be considerable till 50 kilohertz, so maybe after 50 kilohertz, instead of look for a faster readout, maybe I should concentrate on increase the detectable resolution.
Yes. No. Okay. Yes, I understand. So the detectable resolution is yes. Yeah. Okay. But here, if I understood well what Sylvain explained me previously, you don't work with this measurement scheme with this.
Not this, but when no, not this. Okay, but okay, not this. Yeah, you're right. It's not this. but it's in a sort of, I can relate a correspondence. But okay.
Bastien,
Yes.
for this scheme, if you want to increase the resolution, you need to make the spectrum more sharp, right? Sharper.
Yes, but then there is a compromise. If the spectrum is too sharp, you are very sensitive to the environment.
Yeah, of course.
So because your lambda laser can move has a limited range and a limited velocity to move. So there is a compromise.
Yeah. Okay.
So I have a question concerning this. So thank you, Bastien, for your very nice seminar. So you have developed a system for 1 nanometer shift of the Bragg wavelengths.
Yes.
And I'm sorry, I cannot make the. Is it enough, for instance, to have it on an airplane that is flying, or?
I don't remember all the parameters, but with 1 nanometer, you can capture maybe 50 degrees of temperature variation.
Okay, 50.
We have to ask to the specialist.
In composites, yeah.
But a few years ago, we have designed a system for aircraft, specifically for aircraft application, and we had to be to tolerate 2 nanometers, and it was far above the.
There is also the bending. I guess
yes.
It's very huge, the bending, no?
Here, the bending that was applied here, it's yes, quite important.
It's important. I mean, for an aircraft, when you have this, the wings that are very.
Yes, no, on a wing, it's lower than that.
Okay. Thank you.
But here we have characterized. Then we know that with this system we can deal with some situation or no. I cannot say it will work everywhere in every application, but at least we have now the numbers and we know where it works.
Okay, thank you very much.
Bastien?
Yes.
Here is Vincent. Just a very global question. As we are on Friday, I'm a little bit tidy. Maybe you also.
Yes.
My question will be very general. In the 2 first parts of your keynote, you mentioned active and passive tomography. The first one suppose that some PZT elements sense and receive signals, and the other case we are under ambient vibration and ambient excitation. That's it.
Yes.
Could you be able to explain me if one is more performance than the other one? What is your global point of view? Does it make sense to compare one between others? I guess the consequence, if the passive mode works, is to get less expensive material. But I don't know. Could you make a few words in comparison between the?
Yes. Why we started to work on passive? It was really to replace the piezoelectric transducers with FBG.
Okay.
Why is because with piezoelectric transducers we have a lot of wires.
Yes.
And when I was working on aeronautic applications, I didn't thought that it was realistic to embed tens of piezoelectric transducers on an aircraft.
Okay.
That was the main drivers. Then we have tested some passive with piezo, so we can have a simplified electronics. You can imagine a Geronimo system without emission, for example.
Yes, exactly.
Or power consumption. It's you do not inject energy in your system, so you reduce the electronic consumption. But the main advantage is really because I wanted to remove piezoelectric transducers for some application.
Okay, thank
And
you.
in nuclear application, especially, you cannot imagine piezo in your nuclear power plant
Okay.
lasting for 10 years.
So okay, that was I was guessing, that was I was making hypothesis. And the other question was, I don't know if it has a sense, but could you compare, is one is more performant than the other? But I know that this is physical systems are different, but
in general, active is you have better results with active because you have control of
manage. You
Yes,
manage.
you control your emissions,
Yes,
control your source. In practice, we have with a passive in-valve filter or other signal processing approach, we have quite good convergence with. You can see, for example, in the action here. Sorry, with the train, here the reconstruction is a very good signal-to-noise ratio on an industrial configuration. So in practice, passive system works quite. We have detection capabilities quite similar with an active. Just one point is to obtain the convergence, so to have a better signal-to-noise ratio here on this signal. So this signal is more and more similar to this one. You have to wait longer time. So that when we have a lot of noise, typically 1 second of noise is sufficient. And it's sometimes where we have a low amplitude noise, we have to wait 1 minute or 2 minutes. And in that case, performing intercorrelation on 2-minute signals captures at 2 megahertz, you have some limitations for embedded processing. We can do that in our laptop, but
not on Pegas.
But on Pegas, correlation 10 second correlation, I think it doesn't work.
Thank you very
so
much.
far, it's more operational limits than. But it's
thank you.
It depends more on the application we select, active or passive. Okay. Do you have any other question? Or I have killed everyone? Oh, probably you are all dead. Perfect. Oh, Damien.
Okay. So thank you very much, Bastien. So I don't know if Luigi wants to add something. And well, we will compare all this. I hope also, with Xiaoji, who is going to come in Nantes at the beginning of next year, and who is building some reference samples to compare optoelectronics and. Okay, so very interesting topic, this MBG.
But as Luigi said at the beginning, these topics are strongly linked with USES2. That's why we were very happy to be part of the project. And there will be probably not only Xiaoji, but also other interactions within the project with other people.
Yeah, of course, yeah.
So you are welcome to CEA if you know. Those who want to discuss or to make some experiments.
Adil?
Yeah.
Did you see my email? I sent it to you.
Yes. Can you cut the recording? Yes, I've seen it just now because the title of your email was not.
Yeah, because I replied your previous email.
Yes, adapt your title. So I said, oh, it's not important. So I've just read it and okay.
Oh, okay.
Okay. So I guess we will have an answer maybe today. I don't know.
Okay, thank you.
Okay. I hope so. Okay, so
Okay, but
Thank you very much, Bastien.
maybe we
Thank
can
you.
have.
Thank you.
I don't know if maybe we can lighten the screen so that you can take a screenshot or something. No.
for my screen.
No. For all the people who are attending, because we are only black screen. I don't know.
I don't know. Can you see?
Yes, we have to.
Can you see me or not? I'm sure I'm already turned on my camera, but you can see me. I don't know.
No, we cannot see you, Shoji.
But I already turned on my camera. I don't know why.
Okay. So Luigi, you take a screenshot and.
Yeah.
Okay.
Okay. Thank you very much.
Thank you.
Thank you. Bye.
Bye.
Have a
Bye.
nice
Bye-bye.
Bye.
Have a nice weekend. Bye. Thank you, Bastien.
Bye.